Hello, Pre Chemistry. How are y'all doing today? Hopefully y'all are doing well. So today we are going to be continuing our notes in Unit 8, and we're going to be covering VSEPR. All right, now for this, make sure you've got everything. You will need to make sure you have a periodic table definitely for these notes, but otherwise, let's go ahead and get started on this. So what is VSEPR? Well, VSEPR stands for valence shell electron pair repulsion theory, okay? And so we're talking about the VSEPR theory. So what does this mean, valence shell electron pair repulsion? Well, we know that all chemical reactions occur where? Well, they occur in the valence shell, okay? Now, how does that occur? Well, what happens is those electrons, remember, they are either gained or lost, or they're shared, right? And so it is how those electrons will pair up, and as a result of that, we know that there will be some repulsion that occurs. Now, why do you think there would be repulsion? Well, repulsion would be because electrons are negative, and because we've got a bunch of negatives next to each other, they are going to start to push away from each other, okay? So VSEPR is going to be us looking at a molecule, how it's bonded together, and then from there figuring out what shape it would actually make. All right? Now, why would shape matter? Well, the shape of molecules is very, very important for us, right? When you took biology, one of the things that you learned is that a misfolded protein can cause some problems on the inside of your body, right? Well, what makes that misfolded protein do bad things? Well, what happens is it's got the wrong shape. And so with the wrong shape, we get a completely different function. And if we've got a different function, different things are going to happen. So the shape that we've got for molecules is going to be very important because it's going to affect how they interact with the world around them. Okay? Now, the VSEPR theory is going to be the most common way that people talk about the shapes of molecules, all right? And so that is what we are going to focus on learning about, is that actually looking at the most common way and determining what molecules' shapes should actually be. So let's take a look at how we would actually use this in chemistry. So right here, it says determine the geometry, bond angle, and something we call hybridization, which I'll show you how to do that in a second, of the following compounds. So geometry, bond angle, and hybridization of the following compounds. Now, here's something I will say. The geometry and bond angle can actually be found on this second page of your notes. So we've got our bond angle here. We've got our two types of geometry right there. And then you will actually see your hybridization as well. But I'm going to show you how to find hybridization when we're actually doing the, actually drawing the shapes. Okay. So we're going to start with sulfur dioxide. Now, the very first thing that we're going to have to do when we're doing VSEPR is draw the Lewis shape that we've got. So this is either going to be ionic or covalent Lewis structures, right? Typically, it's going to be covalent. And so we need to draw our Lewis structures. So we're going to start with that. So first off, I have sulfur dioxide. So sulfur dioxide is SO2. Okay. So I've got sulfur dioxide. We know that for sulfur, there's one of them. And we know that it has 6 valence electrons. So we've got a total of 6 right there. And then we've got oxygen. There are 2 of them times its 6 valence electrons. So there are 12 right there. So in the grand total, we have 6 plus 12. We have a total of 18 valence electrons. So let's come back over here and let's actually draw the shape. So first off, pick your central atom. So sulfur is going to be my central atom. And we're going to bond our 2 oxygens. Next would be to fill our outer octet. So on this right oxygen, there are currently only 2 electrons. So we're going to add 6. And then on this left oxygen, there are 2. So we're going to also add 6. Now, before we check our central atom, let's count up our electrons. Let's see how many we have. So I have 2, 4, 6, 8, 10, 12, 14, 16. So I have a total of 16 valence electrons. Now, looking back at our original, we're supposed to have 18. So do we have the right amount? No, we do not, right? We need to have 18. So we need to have 2 more. Remember, everything extra can go on the central atom. So we're going to add those 2 extras to the central atom. Okay? Well, now we've got our valence, we've got the correct amount of valence electrons. So now let's actually double check and make sure everything is good. So on my left oxygen, I've got 2, 4, 6, 8 valence electrons. So it's good. On the right oxygen, 2, 4, 6, 8. So it's good. So now let's check our sulfur. So our sulfur has 2, 4, 6. Well, that's not enough, right? We're supposed to have at least 8 on the central atom, unless we're one of those exceptions. So we're supposed to have at least 8. Okay, well, can I just add more dots? No, I can't. Why can't I? Because I don't have enough valence electrons for me to do that. So what is my other option? Well, my other option is to share electrons. So we're going to take and we're going to come over here and we're going to share electrons with that oxygen, which means we have to take 2 of those away because those 2 got shared. Okay, now let's count up everything else again. So I have 2, 4, 6, 8. So that one's good. I have 2, 4, 6, 8. So that one's good. And then for our sulfur, I have 2, 4, 6, and 8. So everything is good there. They've all got 8. And we have 18 valence electrons. So this would be the correct Lewis structure. So now I need to figure out what my VSEPR shape would be. So for my VSEPR, there's something very, very important for you to remember. The reason we draw these shapes like this when we do our Lewis structures is because we're trying to get things spread out as far as possible. Now, why do you think we need to spread them out as far as possible? Well, the answer would be we're spreading them out so far because we're trying to minimize their repulsion. We're trying to minimize that repulsion. Remember, all of these are places where we would find electrons, and those electrons are going to be pushing away from one another. So if we put them on opposite ends, they're going to have the least amount of repulsion possible. Okay? So that's the reason we stretch it all out like that. So what about our shape? Well, there's one other thing that we need to keep in mind, and that would be a lone pair. So here I've got a lone pair on that sulfur. Now, what do lone pairs do? Well, lone pairs are very, very repulsive. So what they do is they're actually going to repulse everything else. They're going to push away everything else. So what does that do to my shape? Well, what it's going to do is it's going to take this and it's going to bend it down. So I'll have my sulfur with its lone pair up there. And then what happens is those 2 oxygens actually get pushed away. And so we get this shape right here. So we've actually taken those 2 oxygens and we've bent them down and away. So what would our shape be? Well, what happened? It started like this and it ended like this. So my shape went from a straight line to a bent line. So we would call this VSEPR shape bent. Okay? So let's actually write out what we've got. So I've got, well, first off, I'm going to make a little key up here at the top to make it a little easier for us. So if I'm talking about the molecular geometry, I'm just going to say that that is mg. Okay? If I've got the electron domain geometry,
Teachers, please release group.
I'm going to call that EDG. If I'm talking about bond angle, I'm going to call that BA. And then last, if I want hybridization, I'm just going to put an H. Okay, that's just to help us out, make it a little bit easier for us to actually write these out. All right, so I've been asked to determine the geometry, the bond angle, and the hybridization. First off, geometry. If they just say geometry, they want both. So in this case, I want molecular geometry and electron domain geometry. So I've got molecular geometry and electron domain geometry. So looking at this, let's actually scroll down here to our shapes. Now, in this case, I've got what we see right here, right? I've got these two atoms, and they're attached to a central atom, and then there is a lone pair up here, okay? So that would be the shape that I would have. So here I have, for my molecular geometry, it is bent. And for my electron domain geometry, it is trigonal planar. So I can now actually go back up and answer those two questions. So my molecular geometry was bent, and the electron domain geometry was trigonal planar. Now it also asks for our bond angle. So for the bond angle, essentially we're just looking and seeing what is the angle between these two oxygens here, right? And then really what's the angle between this oxygen and that lone pair? And what is the angle between that oxygen and that lone pair? So we're looking and trying to figure out what are these angles. Well, there's 3 points to something. If you take a triangle and separate it into 3 sections, then you'll find, a circle and separate it into 3 sections, then what you'll find is that our bond angle is going to be 120 degrees. Now, again, you can go down here to your next page and you'll see, okay, right here with this bent substance, its bond angle is 120. The very last thing that we've got is hybridization. Okay, so for our hybridization, what we're going to do is we're going to actually use our hands to figure out what the hybridization is. Now, remember that with hybridization, really what it's coming down to is where are our orbitals? So where are those electrons sitting? Okay, so what I use is I use my hands and my fingers on them to help me determine what is the hybridization of a substance. So first off, remember that your S sublevel holds 2 electrons. And so in that 2 electrons, in that S sublevel, we've also got 1 single orbital that's there, right? And so that 1 orbital can hold both of those electrons. So hybridization is talking about those orbitals, and what we're going to do is represent those orbitals with our fingers and with that hybridization, okay? So we have S, remember that can hold 2 electrons, P, 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 and then we're going to go D, and then last there's going to have another D just right here. Just imagine I have a 6th finger sticking out right here. Okay, so S, P, 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 D, and D. And that's basically what we're going to do for our hybridization. Now, how do I actually use that? Well, essentially what you do is you look and see how many things are attached to that central atom. So I've got 1, 2, 3 things attached, and so I would go SPP. So SP2. Okay, so S and there would be 2 P's. So for that, our hybridization would be SP2. 2 because there's going to be 3 things attached to that central atom. Okay? All right. So let's take a look at another one. So I'm going to actually move a lot faster going through when we're drawing our Lewis structures for the remainder of this. So I have carbon monoxide, CO. I have carbon, which is, there's one of those, times 4. It's 4 valence electrons. I have oxygen. There's one of those, times the 6 valence electrons. So we would have a total of 10 valence electrons. So then how can I pick a central atom if there's only 2 elements? Well, there's not going to be a central atom. They're going to be side by side. Fill our outer octets. Okay, we get that. Now let's count up our electrons. So I have 2, 4, 6, 8, 10, 12, 14. Now looking back, we should only have 10. So we've got too many electrons. So what we do is we're going to end up sharing some. So we're going to take 2 away and we're going to share those. Well, what that means is that we can then take these over here away as well, right? Because then we're going to have, sorry, it's not drawn for me. So 2, 4, 6, and 8. Same thing on my carbon. So let's count up our electrons again. So I have 2, 4, 6, 8, 10, 12 now. But again, we're still not quite there, so we would need to share some more. Take that, share, take those 2 away to share, and then we're going to take 2 away from there because they don't need to be. And now we would count up our electrons one final time. 2, 4, 6, 8, and 10. So we would have the right amount of electrons now. Okay, so this would be our Lewis structure. Now, looking at this, there's not really any way that these are going to spread out any further, right? They're sitting side by side. And so since they're sitting side by side, we can't change that. Well, what does that look like? That looks like a line, right? Well, so since it looks like a line, the molecular geometry for it would be linear. So molecular geometry is linear. The electron domain geometry is also going to be linear. My bond angle, well, looking at that, what is going to be the angle from here to here? Well, it's essentially halfway around a circle, right? So we've got 180 degrees. And then our hybridization. So for hybridization, remember that's how many things are attached. So if I'm taking this oxygen, there is one thing here, and then there is this bond between. Now remember that the bond between is a single bond, right? So if it's a single bond, a double bond, or a triple bond, one way or another, it is still just one bond. It is a triple bond, a double bond, or a single bond. Okay? So our hybridization, we've got 2 things attached. So we have SP as our hybridization. And again, you could look at the table at the back on your second page. It looks like this. Your hybridization is over here. Okay? All right, so I actually want y'all to give this one right here a try. So go ahead. You're going to need to draw your Lewis structure. See if you can get them spread out, and then see if you can, based off of the table on the back, predict what the shape, the molecular geometry, the electron domain geometry, the bond angle, and the hybridization would be. Okay, so pause your video, work through that, and then we will go over it. All right, so this is what you should have ended up with. So you should have ended up that this is a tetrahedral for its VSEPR shape, for its molecular geometry. Its electron domain geometry would also be tetrahedral. The bond angle is 109.5. Now, my guess is y'all probably looked at this and they're like, okay, well, this is a 90-degree angle, right? Well, yes, that looks like a 90-degree angle. But remember, VSEPR shapes are going to be in a 3D environment, okay? And so this is actually going to be what you would see with a tetrahedral. So the molecules themselves are going to be spread out a little bit more. So looking at my angle here, this is actually 109.5 degrees instead. And that's because that's the most that we can spread it out across a 3D, a three-dimensional environment. Okay, so that's why we would get that shape there. All right, so I want y'all to again give this next one a try. And so pause your video, give this next one a try, and then we will go over it as well. All right, so here is what you should have ended up with this. So first off, you probably looked at this and you're like, okay, well, there's 3 little legs coming off of it, right? So you would kind of think in something like this, where there's just kind of 3 legs coming off of it, and that's that. But you've also got to remember that you added that lone pair. Now, what did I say for the lone pairs? I said that lone pairs are very, very repulsive, right? And so because they're very, very repulsive, what we're going to end up seeing is they're going to take this, and it's actually going to push the rest of these down and away. All right, and so I'm going to actually turn it down. So you see how it stands up just a little bit there? So that's because it is going to be forming that like a 3-sided pyramid, okay? Versus what you probably originally thought, which is this, right there. So see how that lays flat on there? So that would be what we would call trigonal planar. But this is what we should have ended up with. All right, so that would be why we got that trigonal pyramidal shape. Looks like a little pyramid. And then we find our bond angles to be the same as what we had with tetrahedral, so 109.5. And then last thing is the hybridization, which remember the hybridization is how many things are attached. So we have 1, 2, 3, 4. So we take our hand, S, P, 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 okay, which would be SP3. All righty. So I am actually going to leave the rest of this for y'all to do as practice. As always, let us know if y'all need anything, and hopefully y'all have a great rest of the day. Bye, y'all.